Okay, moving on to the third page here of the sample exam. Just lined up. Okay, two problems on this next page, both dealing with kind of chapter 10, intermolecular interactions and how that relates to structure. So number 3 here, we're given a molecular formula, C6H14O. We're told it can be represented by multiple structures, but we only need to think about two of them. We want to draw two isomers of this formula. So isomer, same formula, different molecule, so a different chemical structure that would be expected to have markedly different boiling points. Now, I think that's key here. What I'm really looking for here, if I say markedly different or very different boiling points, I want to see molecules that would have different types of intermolecular interactions. You'd have a different boiling point if you had different surface areas within two isomers from one to another. But to have a really big difference, right, I want to see different types of intermolecular interactions. So in this case, because there's oxygen in this molecule, we have the potential to have hydrogen bonding. If we connect a hydrogen to that oxygen, that's a strong intermolecular interaction that should lead to a higher boiling point than in a molecule with the same formula that doesn't have hydrogen bonding. So that's the distinction I would want here. We'll draw one molecule that can have hydrogen bonding interactions, right? And in that case, we'll just connect all the carbons, 6 carbons, and then we'll put the oxygen kind of on the end of that chain so we can put a hydrogen there. That part of the molecule will mean there's hydrogen bonding. We have enough hydrogens here to give 4 bonds to all of the carbons. So we'll put 2 on each of the carbons here in the body of this chain. The one on the end needs 3 more bonds, so 3 hydrogens there, right? And that's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and the 14th is there on the oxygen. Now, oxygen doesn't just have 2 bonds, it's also got 4 non-bonding electrons, or you could say 2 lone pairs of electrons. But that molecule is going to have hydrogen bonding. That's going to have a high boiling point for this set of molecules. So that's the one I want to put the box around or the circle around. Now, the other one, to make the boiling point low, I don't want hydrogen bonding. Now, if I'm thinking I really, really want it to be low, right, more branching would mean less surface area. That would minimize the types of London interactions you could have as well. So let's put the oxygen in the middle, right, which means we're going to have a carbon on each side. Right, but then let's also put some branches in here to keep the surface area down. So I'll put the carbons branched like that. Right now, as long as this one's got hydrogen bonding, this one doesn't, you have definitely answered the question correctly, right? But I'm not limited to just having you draw 2, right? I could have you draw 4 here, where you'd want to draw 2 different ones with hydrogen bonding, 2 different ones without, and then have a big enough surface area difference that you could still tell the difference between their boiling points. Now, in this case, carbons on the ends here each need 3 more bonds. So I can put 3 hydrogens on each of those. That will use up 12 of the total hydrogens. And then the carbons here where we did the branching, they have 3 bonds already, so they would each need 1 hydrogen. Right? So that compound is going to be polar because this oxygen would have a bent geometry or bent shape around that oxygen because it does have 4 sets of electrons. Even though I drew it like it's linear, it is not linear, right? And that's certainly something you should recognize. Certainly by the time you're ready to take the test, I hope that you would recognize that. So this is a polar molecule that there'd be dipole-dipole interactions, but much weaker interactions than we see here. And in fact, in this case, with these kind of branched carbon groups, it would be really hard to get close to that oxygen. It's kind of blocked by the size of the 2 carbon groups attached. So this would have really weak intermolecular interactions, would evaporate really quickly, and have a very low boiling point. Okay, I think we can get number 4 here into the same video, and number 4 deals with similar issues, although a little bit different because now we're talking about mixing molecules together. So first off, we're just given the observation iodine, I2, is slightly soluble in water. And part A here, we're asked to draw and describe the relevant interactions that allow the above observation. Now, to do that, we'd need the Lewis structures. So iodine, just two iodine atoms make up that molecule. So it's kind of this trivial linear structure where they're connected together. But you would have enough electrons to fill in the octets on the two iodines. But what's kind of important for this question is that is nonpolar. Right? Iodine has the same electronegativity as iodine, so this is a completely evenly shared bond, or a nonpolar covalent bond. So that's a nonpolar molecule. Now, what we know about intermolecular interactions is that like tends to dissolve like when it comes to liquids mixing together. So polar compounds will mix easily with other polar compounds, and nonpolar compounds will mix easily with other nonpolar compounds. But the reason why we have to think about why iodine would dissolve in water is because water is polar, right? We said back up here, number 3, oxygen is bent. It's bent here in water as well. That means it's negative on the oxygen side, oxygen being more electronegative, pulling the electron density away from the hydrogens in terms of their shared electrons. And then it's positive on the other side of the molecule where the hydrogens are, or on the hydrogens themselves. So it's polar. So this kind of general like dissolves like would tell us, no, these should not mix together, right? And that's really why the slightly is in there. Iodine is not super soluble in water. You can dissolve a little of it, but not a whole lot. But the reason you can dissolve a little of it is because of inducing a dipole. So imagine here, let me just draw another water molecule here. Right? I'm going to leave off the lone pairs just for clarity of structure. It's negative on the oxygen side. Right? Maybe this is at the surface of a sample of water and we're dropping in some solid iodine. Well, an iodine molecule comes close by. Now, let me say it's oriented this way as it comes close by. Right? The electrons in this iodine molecule will start to experience the electrons that are pulled over to the negative side of the water molecule when the molecules get in close proximity to each other. So this negative charge on the polar water molecule will induce a dipole in the iodine. So the electrons on the kind of lower side, the way I have it drawn, will be pushed away by the negative charge, and that'll leave the iodine molecule positive on that side that the electrons fled from or moved away from, negative on the other side where the electrons went. So that is an induced dipole, if I can spell. Right? So now there's a little bit of a dipole to go along with the polar water molecule. This is why this helps the iodine dissolve in the water. So we can dissolve a little bit of iodine by inducing a dipole in the sample. Okay. Now part B says predict what would happen, right, and justify the prediction if the aqueous iodine solution was treated with carbon tetrachloride and shaken. Right? Now carbon tetrachloride, 4 chlorines around a carbon, is going to end up being tetrahedral. Right? Now, you might draw the structure first, realize it's got 4 bonds, 4 sets of electrons. I made one too many dots there. But you should get to the point where you recognize it's a tetrahedral. So even though chlorine is more electronegative than carbon, right, each of these bonds is having its electrons pulled away by the chlorine. But since it's a symmetrical molecule and the electrons are being pulled in all of the directions, this is nonpolar molecule, right? So now if we mix the carbon tetrachloride with the water, right, large amounts, one's nonpolar, one's polar, they're not going to mix together. Maybe a little bit right at the edges of the solutions where we could induce some dipole in the carbon tetrachloride, but mostly they're going to stay separated because they have different properties. Well, iodine, being nonpolar, is going to be much more soluble in the nonpolar liquid than it is in the polar liquid, the water. So what's going to happen is I2 will move to be dissolved in the nonpolar carbon tetrachloride. Right? So the iodine will no longer be in the water. It'll be only in the carbon tetrachloride, and the water will be kind of all iodine free there in the sample. All right, stop the video there. We'll pick up with a new one on the next page.